So finally, we're ready to start testing our research questions statistically. While it took us a while to get here, our earlier steps should never be avoided. That is, no matter how sophisticated you may become as a quantitative researcher, you'll always need to examine your codebook, manage your data, and examine descriptive statistics for the variables of interest.
In the description of hypothesis testing, when we looked at the association between depression and smoking, we were working with a categorical explanatory variable, the presence or absence of depression, and a quantitative response variable, the number of cigarettes smoked per month. When you're testing hypotheses with a categorical explanatory variable and a quantitative response variable, the tool that you should use is analysis of variance, also called ANOVA.
Now that you understand in what situations you would use ANOVA, we're ready to learn how it works, or more specifically, what the idea is behind comparing means. The test that you'll be using is called ANOVA F-test. So let's use another categorical to quantitative research question.
Is academic frustration related to major? In this example, a college dean believes that students with different majors may experience different levels of academic frustration. Random samples of 35 individuals, each of business, English, mathematics, and psychology majors, were asked to rate their level of academic frustration on a scale of 1, the lowest, to 20, the highest.
This figure highlights that we'll be examining the relationship between major, our explanatory or X variable, and frustration level, our response or Y variable, to compare the different means of frustration levels among the 4 majors defined by X. The null hypothesis claims that there's no relationship between the explanatory and response variables X and Y. Since the relationship is examined by comparing the means of Y in the populations defined by the values of X, no relationship would signify that all the means are equal. Therefore, the null hypothesis of the F-test is population mean 1 equals population mean 2 equals population mean 3 equals population mean 4. Here, we have just one alternative hypothesis, which claims that there is a relationship between X and Y, the explanatory and response variable. In terms of the means, it simply says the opposite, that not all of the means are equal, and we simply write H subscript A, not all the population means are equal. There are many ways for the population means not to be equal. We'll talk about that later. For now, let's think about how we would go about testing whether the population means are equal. We could calculate the mean frustration level for each major and see how far apart those sample means are, or, in other words, measure the variation between the sample means. If we find that the 4 sample means are not all close together, we'll say that we have evidence against the null hypothesis. And otherwise, if they are close together, we'll say that we do not have evidence against the null hypothesis. This seems quite simple, but is this enough? Let's see. It turns out that the sample mean frustration score of the 35 business majors is 7.3. The sample mean frustration score for the 35 English majors is 11.8. The sample mean frustration score for the 35 math majors is 13.2, and the sample mean frustration score for the 35 psychology majors is 14.0. Here's a graphical representation of 2 hypothetical data sets taken from 2 different populations. For instance, students in country 1 and students in country 2. In our hypothetical samples, the means are the same, but they appear in this box plot very differently. A box plot is a convenient way of graphically depicting groups of numerical data, including such descriptive information as the smallest observation of the group, the mean and median, the largest observation, and the spread or variability of the values. The top of the line that sticks out of the top of the box plot and the bottom of the line that sticks out at the bottom of the box plot are the highest and lowest values. The red dot is the mean. The middle horizontal line is the median. You can see that each data set has the same set of means, and thus the same differences among them. That is, students in Country 1 and students in Country 2 both show data for 4 groups with the sample means of 7.3, 11.8, 13.2, and 14.0, indicated with red marks. The important difference between the two data sets is that the first represents data with a large amount of variation within each of the 4 groups. The second represents data with a small amount of variation within each of the 4 groups. Box plots for Country 1 show plenty of overlap among the 4 groups because of the large amount of variation in frustration scores within the groups. One could imagine the data arising from 4 random samples taken from 4 populations, all having the same mean of about 11 or 12. The first group of values may have been a bit on the low side, and the other 3 a bit on the high side, but such differences could conceivably have come about by chance. This would be the case if the null hypothesis claiming equal population means were true. Box plots for Country 2 show very little overlap because of the small amount of variation in frustration scores within the groups. It would be very hard to believe that we're sampling from 4 groups that have equal population means. This case is an example of when the null hypothesis claiming equal population means would be false. The question we need to answer with the ANOVA F test is, are the differences among the sample means due to true differences among the population means, or merely due to sampling variability? In order to answer this question using our data, we obviously need to look at the variation among the sample means, but that's not enough. We also need to look at the variation among the sample means relative to the variation within the groups. So F is the variation among sample means divided by the variation within groups. In other words, we need to look at the quantity, variation among sample means, divided by variation within groups, which measures to what extent the difference among the sampled groups means dominates over the usual variation within sampled groups, which reflects differences in individuals that are typical in random samples. When the variation within groups is large, like in Country 1, the differences or variation among the sample means could become negligible, and the data would provide very little evidence against the null hypothesis. When the variation within groups is small, like in Country 2, the variation among the sample means dominates, and the data have stronger evidence against the null hypothesis.
Looking at the ratio of variations is the idea behind comparisons of means, thus the name analysis of variance.
Here are the results of the analysis of variance for Country 2, testing the relationship between major and frustration score. The F statistic, circled in red, is 46.6. Since we know this is the variability among sample means divided by the variability within groups, this large number suggests that the variability among sample means is much greater than that within sample groups. The p-value of the ANOVA F test is the probability of getting an F statistic as large as we got, or even larger, had the null hypothesis been true. That is, had the population means been equal. In other words, it tells us how surprising it is to find data like those observed, assuming that there is no difference among the population means. This p-value is practically 0, telling us that it would be next to impossible to get data like those observed had the mean frustration level of the 4 majors been the same as the null hypothesis claims. The p-value of 0.0001 suggests that we will incorrectly reject the null hypothesis 1 in 10,000 times, and we will be correct in accepting the alternate hypothesis 9,999 times out of 10,000 times. So we can confidently conclude that the frustration level means of the 4 majors are not all the same, or in other words, there's a significant association between frustration level and major. So we accept the alternate hypothesis and reject the null hypothesis. Now that you have a feel for analysis of variance, we'll run the test using R. We'll use an example first described in hypothesis testing. Is major depression associated with smoking quantity among current young adult smokers? Or, in hypothesis testing terms, are the mean number of cigarettes smoked per month equal or not equal for those individuals with and without major depression? The explanatory variable here is categorical with two levels, that is, the presence or absence of major depression. The response variable, smoking quantity, measured by the number of cigarettes smoked per month, ranges from 1 to 2,940. Returning to the R program we've been building to examine our NESARC data, let's quickly review the program pieces once again. First, we have our command that reads in the dataset. Next, we create a subset of the dataset containing only the sample we want to use in our sample research topic, which is young adult smokers. We also added labels to help read the output easily and set appropriate missing data. Then we created secondary variables measuring usual smoking frequency per month, number of cigarettes smoked per month, and also packs of cigarettes smoked per month as both a quantitative and a categorical variable. As you know, all the commands below data management are requesting specific output or results. This is where we'll need to add the syntax for analysis of variance. To conduct an analysis of variance, we're going to use the AOV function. We start with AOV parentheses. The main input to this function is a formula that describes the relationship between the variables that you're evaluating. This formula takes the form of response variable tilde explanatory variable. The name of the response variable is numsigmo_est, and the name of the categorical explanatory variable is major dep life. So the formula within the parentheses is numsigmo_est tilde major dep life. The second input to the AOV function is the name of your data set. Specifying data equals sub1 as the second input to the AOV function after the formula means that we're telling R in which data set to find these variables, and then we don't have to keep typing $1 before each variable name. Finally, we're using the assignment arrow to store the results of the AOV function into a new workspace object called numsig.aov. As with all assignments, anything on the left of the arrow is a new object you're creating, and you can name this anything you want. We're calling it numsig.aov because this name describes the response variable and the type of statistical test we're running. The reason we're storing this into a new workspace object is so we're able to access it later using different functions. When we run this line, R doesn't output anything in the console window. That's because all the results are stored in the new workspace object we just created, called numsig.aov. To access the important results, we need to use the function summary on the ANOVA object numsig.aov. Looks like this: summary parens numsig.aov in parens. Now we're ready to run the program and take a look at the output. Running the summary function of our AOV object first displays an analysis of variance table. This table includes the name of the categorical explanatory variable, degrees of freedom, which is the number of different values or levels of the class variable -1, the F statistic, and the p-value that corresponds to the F statistic. So here we see our categorical explanatory variable, major dep life, has 1 degree of freedom, meaning 2 levels. Our calculated F statistic, called the F value in this output, is 3.55. The significance, probability, or p-value associated with this F statistic is labeled PR parens greater than F close parens. And as you can see, the p-value is 0.0597, just over our p-value 0.05 cut point. The summary function then displays the visual code for the p-values. If you see asterisks in the analysis of variance table, this is an immediate visual indicator that you have a significant p-value according to these codes. In this case, the visual code is a dot, which corresponds to a p-value between 0.05 and 0.10. Finally, the output tells us how many observations were deleted because they contain NAs, or missing data. Because the p-value is greater than 0.05, namely 0.06, we're going to accept the null hypothesis and say that these means are equal and that there's no association between the presence or absence of major depression and the number of cigarettes smoked per month among young adult smokers. If we chose to reject the null hypothesis, we would be wrong 6 out of 100 times. And again, by normal scientific standards, this is not adequate certainty to reject the null hypothesis and say that there is an association. Instead, we're going to accept the null hypothesis and say that there's no association. Had the p-value been less than 0.05, we would know that there was a significant association. With a significant p-value, we could have said that young adult smokers with major depression smoke significantly more cigarettes per month than young adult smokers without major depression. After running an ANOVA, you may want to run some follow-up descriptive statistics for the mean level of the response variable for every level of the explanatory variable. Since ANOVA tests whether these group means are significantly different, for example, whether the mean smoking quantity differs across groups of people with different depression status, you may want to look at what those means are. You can do that with the following by command. This command calculates the mean of the response variable by every level of the categorical explanatory variable. The third option specifies that calculation, which in our case is mean, because we want to calculate the mean value of num sigmo underscore est for every level of major dep life. The final option, na.rm equal t, tells R to remove NAs before calculating a mean, so that R is able to perform that calculation. So you can see that the mean number of cigarettes smoked per month among individuals without major depression is about 313, while among individuals with depression, it's 341. And you know from the ANOVA result that these are not significantly different from each other. So we've shown you the ropes in terms of a categorical explanatory variable that has two levels, as it did here with depression. For this interpretation, all we need to know is the p-value and the means for each of the two groups.
But what if my categorical explanatory variable has more than two groups? In this example, I'm going to examine the association between ethnicity and smoking quantity.
The explanatory variable, ethnicity, actually has 5 levels or groups. 1 is white, 2 is black, 3 is American Indian, Alaskan Native, 4 Asian Native, Hawaiian Pacific Islander, and 5 Hispanic or Latino. So by running an analysis of variance, we're asking whether the number of cigarettes smoked differs for different ethnic groups. Since we're only changing the categorical explanatory variable, that's the only part of the AOV command that we'll need to change. So rather than including major dep life in the formula part of the command, we're going to include ethrace2a. Again, we're assigning the results to a new workspace object. We're giving it a different name here that indicates that this is the ANOVA with ethnicity. If we give it the same name as before, R will overwrite the previous ANOVA object without warning. Here are the ANOVA results for a greater than 2-level explanatory variable. You will notice that R's output is actually scientific notation. This time the F statistic is 24.4 with an associated p-value of less than 2.2 times 10 to the minus 16th power, which actually means a decimal point followed by 16 zeros and then a 2. This is the smallest p-value R calculates. It means that the p-value is less than 0.0001.
Well, this tells me that I can safely reject the null hypothesis and say that there is an association between ethnicity and smoking quantity.
The f-test and the p-value do not provide insight into why the null hypothesis can be rejected because there are multiple levels to my categorical explanatory variable. They do not tell us in what way the population means are not statistically equal.
Note that there are many ways for population means not to be all equal. Having each of them not equal to the other is just one of them. Another way could be that only two of the populations are not equal to one another. In the case where the explanatory variable represents more than two groups, a significant ANOVA does not tell us which groups are different from the others. To determine which groups are different from the others, we would need to perform a post hoc test. A post hoc test conducts post hoc paired comparisons. Post hoc means after the fact, and these post hoc paired comparisons must be conducted in a particular way in order to prevent excessive type 1 error. Type 1 error, as you'll recall, occurs when you make an incorrect decision about the null hypothesis. That is, you reject the null hypothesis when the null hypothesis is true. Why can't we just perform multiple ANOVAs? That is, why can't we just subset our observations and take two at a time? That is, compare white versus black, white versus American Indian, Alaskan Native, etc., until all the paired comparisons have been made. As you know, we accept significance and reject the null hypothesis at p less than or equal to 0.05. A 5% chance that we're wrong and have committed a type 1 error. There's actually a 5% chance of making a type 1 error for each analysis of variance that we conduct on this question. Therefore, performing multiple tests means that our overall chance of committing type 1 error could be far greater than 5%. Here's how it works out. Using the formula displayed under this table, you can see that while one test has a type 1 error rate of 0.05, by the time we've conducted 10 tests on this question, our chance of rejecting the null hypothesis when the null hypothesis is true is up to 40%. This increase in the type 1 error rate is called the family-wise error rate and is the error rate for the group of pair comparison.
Post hoc tests are designed to evaluate the difference between pairs of means while protecting against inflation of type 1 errors, and there are a lot of post hoc tests to choose from when it comes to analysis of variance. There's the SIDAC and the Holm t-test and Fisher's least significant difference test, Tukey's honestly significant difference test, the Sheffey test, the Newman-Cools test, Dunnett's multiple comparison test, the Duncan multiple range test, and the Bonferroni procedure. It's enough to make your head swim.
While there are certainly differences in how conservative each test is in terms of protecting against type 1 error, in many cases, it's far less important which post hoc test you conduct, and far more important that you do conduct one. In order to conduct post hoc paired comparisons, in the context of the ANOVA examining the association between ethnicity and number of cigarettes smoked per month among young adult smokers, we will use the Tukey HSD test. To do this, we use the function Tukey HSD on the ANOVA object. So the formula is going to look like this. Tukey HSD parens numsig.eth.aov in parens. This command provides the formula you used in your original ANOVA analysis. Next, it names the explanatory variable in that formula, followed by a table of pairwise differences. Here's how to interpret the table. There's one line for each possible pair within the ethnicity variable. For example, black versus white, Hispanic versus white, Hispanic versus black, and so on. And for a 5-level categorical variable, there are 10 pairs. This table shows the differences in means, so the first entry in each line tells you which level is being subtracted from which other level. The first line says 2 minus 1, So if we go back to our code book, that means it's subtracting the mean smoking quantity for white individuals from the mean smoking quantity for black individuals. The next number is the actual difference between the groups, which is negative 109. Since this is negative, this means that whites, on average, smoke 109 more cigarettes per month than blacks. The next two columns represent the confidence intervals of this value. That is, we know that the difference for the sample is negative 109, but due to random sampling, for the entire population, this number could fall anywhere between the lower bound of negative 164 and the upper bound of negative 54. Most importantly, the right column contains the adjusted p-value. This p-value is already adjusted for multiple comparisons, so you can compare this to the standard alpha value of 0.05. So, going through these 10 pairwise comparisons, you can see that some groups have significantly different means of smoking quantity, while others do not. Since there are 3 pairs with an adjusted p-value below 0.05, there are 3 significant pairwise differences here. Specifically, whites on average have a higher smoking quantity compared to Black, Asian, and Hispanic Latino individuals. But none of the other comparisons are significant. For example, Black and Hispanic Latino individuals do not smoke significantly different amounts on average. We've covered a lot of information, so here's a quick summary of analysis of variance. First, an analysis of variance is used when we have a categorical explanatory variable and a quantitative response variable, and we want to examine differences in the mean response variable for each category of our explanatory variable. The null hypothesis is that there's no relationship between the explanatory and response variable. In other words, that all means are equal. The alternate hypothesis is that not all means are equal. The F statistic is calculated by comparing the variation among sample means to the variation within groups. If the variation among sample means wins out, the p-value will be less than or equal to 0.05, and we have a significant finding. This would allow us to reject the null hypothesis and say that the explanatory and response variables are associated. The Model R syntax for conducting an analysis of variance is the function AOV. The AOV function first requires a formula describing the relationship between the variables that you want to test. Here's the model for that formula: response variable, tilde, explanatory variable. Second, the AOV function requires a pointer to the data set so that R knows where to find the variable names. We store the result into a new workspace object, which we need to input into the summary function to see the results. We often will want to examine the group means to help better interpret the results of the ANOVA, which we can do with the by function. If your explanatory variable has more than 2 levels or groups, you'll also need to conduct a post hoc test. To conduct Tukey's honest significant difference test, input the ANOVA object into the function Tukey HSD. Now you're ready to test a categorical to quantitative relationship. If your own research question does not include these types of variables, you might want to test the procedure with variables from your data set that do require an ANOVA. For example, you could look at mean age differences according to any categorical variable in the NESARC, or treating the grade level variable in add health as quantitative, you could look at mean differences in grade level, again, by any categorical variable that you choose. For both Gapminder and the Mars Crater data, there are many quantitative variables, so you might choose to categorize one of them for inclusion in an ANOVA. Whatever types of variables you have, you'll be able to test the association with the right tool.